In March, in March 19th, it feels. In March 2020, the Mississauga Center had its last meeting here. It was a potpourri. And that was the Friday before the Monday where everything locked down. So,
Yeah, you might want to stand over here.
oh, well, why do they want to see me?
Well,
There I am. Hello. Well, they can also see there is a camera back there which gives a wide angle. So actually, all of you are in the view as well.
the back of your head.
Yeah, yeah. All right. So for those who are new, my name is Randy Atwood. I am the president of the Mississauga Center. And after about a year-long effort, we are very pleased to be holding meetings back at the University of Toronto Mississauga. So our meetings we have 2 meetings a month normally, a speaker night, which is our night tonight, and then what we call a potpourri, where there are short talks on various subjects. And let me tell you about Sheila. All right, that's going to be recorded. So our potpourri meeting is where members give short talks on various subjects. Part of our efforts to come back and hold meetings here at UTM will involve joint meetings between the RASC and UTM. And we're hoping that we can work with the chemistry and physical sciences faculty and the astronomy group and the physics club to organize talks where we bring in people, whether locally or distant, and really start an interesting series of presentations. And then for the potpourri, it'll give an opportunity for RAC members and UTM students, if they wish, to come out and just give some short talks on various things that they're interested in and what they're doing. So it'll be a collaborative effort, and we look forward to it very much. We did have a star party out in the north playing field a few weeks ago, and we had about I don't know 200 students out looking at Jupiter and Saturn, and that was a lot of fun. So our hope is that we can sort of work ourselves into being part of the UTM family. We've been doing this here in not this room, but in various rooms along here for nearly 20 years. It was April 2003 when we held our first meeting here. And so we're very glad to be back. I'd like to introduce a few people just for our new members, because we have over 200 members in our center, but many of them are new, and some of them I'm sure are here tonight. So I want to introduce our council. Again, my name is Randy Atwood. I'm president. Our vice president is Alan Connery. Our treasurer is Anil Mathur. Okay. And Anil has been selling calendars tonight, if you're interested in our RASC calendars. Our secretary is Swapna Shrivastava. Our past president is Steve Malia. I should mention that Steve is one of the remaining telescope vendors in the GTA. So he's very rare. There aren't. Are there any others around now? Or very. Not that matter. There we go. Yeah. So talk to Steve if you're in the market. Our council, Val Connery, Betty Robinson, Kirby Alguire, Rob Neal. He's not up. Remotely, Chris Malicki.
Hello, everybody.
Oh, there he is. And our honorary president is, many of you know, Dr. Ulrich Krull. He's had a long affiliation with the university. All right. So our speaker tonight is Dr. John Percy. I must admit, I've known John for quite a while. I actually met him not long after I joined the society, so it's been many years. John is, I would say, a brilliant educator and someone who has really given the RASC support over the decades. He graduated at the University of Toronto. He was a gold medal winner at the University of Toronto back in the early 60s. And he joined Arundel essentially when it opened in 1967. So he has been here from the beginning. He's currently Professor Emeritus in Astronomy and Astrophysics and Science Education at OISE. So he's been involved with OISE for a long time. He retired recently, but still I find all the astronomers that I have known, once they retire, they just keep doing the same thing. I don't know if they're getting paid for it, but they seem to still have an office somewhere and they just continue to do what they do. So John has been really affiliated with the RASC. He's been a past president, editor of the journal, editor of the Observer's Handbook. His research has been variable stars. So recently, I don't know if John is still journal editor of the AAVSO journal, but recently he was recognized at our General Assembly in 2019 and involved with the IAU area of astronomy education. I could go on, but he was our honorary president recently. And was really one of the sponsors that brought us into UTM nearly 20 years ago. So a good friend, and I reached out to him to be our first presenter when we returned here to UTM. So I'm going to see if John is there. Are you there? Oh, he's there. Oh my gosh. All right, let us turn down the lights and then you're good to go. I'm going to try to mute everything that I can mute.
But can you hear me?
Can you hear me?
I can hear you, but can you
Okay,
hear me?
you're coming in 5. Give me 30 seconds and then start. Okay, John, we're all set.
Okay, thank you very much. So particular thanks to Randy and all the other people there who made this evening possible. I rather wish I was back at UTM right now. My schedule didn't quite allow for that. I haven't actually been to UTM since before the pandemic, except once to go to a vaccination clinic that was held in our recreation center. But I do hope to be back soon. You may know that, and you may not know if you're new to the RASC Mississauga, that UTM has had an illustrious history of astronomy and some very important contributions. I won't go into them right now, but if you can go to the RASC journal for December 2016, I wrote one of my columns on all of the astronomical achievements of UTM and its faculty. So I refer you to that. So Tonight I was asked to give my misconceptions talk. This is a talk that I usually give to the general public in libraries and places like that. And it may well be that since most of you out there are amateur astronomers, then most of you will not have the misconceptions that I introduce you to tonight. On the other hand, I know that you do really great work in public education. And so what I tell you tonight may be helpful in dealing with the general public or your friends or your neighbors or your family or whatever. Okay. Right. So let's start out by what is an astronomical misconception? Well, it's something that people know or think they know about the universe that's not correct. I mean, there's lots of things about the universe that I don't know, and I don't claim to know about them either. And so there's many different kinds of misconceptions. And I'm going to try and point out in most of these cases here where the misconceptions come from, because there are many other fields, including what's happening on the news every day, where there's lots of misconceptions, fake news, and things like that. So it's important to know what it is that leads to misconceptions like this. We can certainly start out with misconceptions about astronomers. So on the left there, a famous cartoonist from Mississauga, Unger, showing the typical astronomer, a graying white male gazing up at the sky, like this one is doing. Or if you prefer the one at the bottom right here, who's got a funny hat on and staring through a telescope out into space, looking as if he's casting somebody's horoscope. So this is certainly not what astronomers are all about. And one thing I want to do is to introduce you to some of my colleagues at the Dunlap Institute of the University of Toronto, just to show how diverse astronomy is these days. Anybody can be an astronomer. I've always hoped that amateur astronomy can be just as diverse as professional astronomy is getting to be, as you see in this picture here. So on to the granddaddy of astronomical misconceptions, and that is simply, why is it warm in the summer? Well, here's some possibilities here. I won't ask you to vote on this, but I will tell you that the vast majority of the public will choose the first one, that the Earth is closer to the sun in the summer and further away in the winter. That turns out to be the opposite, by the way, simply because that's the thing that makes most sense to us. In fact, the reason that it's warm in the summer is because the sun is higher in the sky. We get direct sunlight coming down, not directly down. The sun is not directly overhead in our latitudes. And also the obvious thing is the days are twice as long in the summer as they are in the winter. So you're all familiar with the paths of the sun during the year. And in the winter time, the sun rises far to the south of east, spends maybe 8 hours above the horizon, whereas in the first day of summer, it goes way high up in the sky, sets to the north of west, and stays above the horizon for something like 16 hours. So why this misconception? Well, I'm showing you here a diagram from a typical textbook. And everything is wrong with that diagram you could possibly imagine. First of all, it's two-dimensional instead of three-dimensional. The scale is totally wrong. It looks as if the Earth is almost as big as the sun, and the distance away from the sun is almost as big as the sun itself. And so it's totally wrong. But if you look at a diagram like this, it's obvious that the Earth has to be warmer when it's at this position shown here on to the right of the sun here. And when it gets over to the other side of its orbit, it's obviously going to be further away. Well, the fact is that the Earth's orbit is very close to being circular. So it's not that, despite the fact that that might be the most obvious answer. So here's another misconception. Why is it that the moon shows phases? Well, most people on the street would somehow think it was because the moon moved into the shadow of the Earth. That's not the case. The moon shows phases because as it goes around the Earth, the orientation of the sun, the Earth, and the moon changes as the moon goes around. The best way to demonstrate that is with hands-on demonstrations like this one here. Certainly that's the best way to do it in the school. It'll be a bit harder to do it during a star party or whatever. But again, there's many things wrong with the sort of diagrams that we use to show the phases of the moon. It really does look as if the moon is moving through the shadow of the Earth. And here's about the worst possible textbook diagram that you could possibly imagine. Everything is wrong with this. It looks as if the moon's orbit is highly elliptical. That's because they don't tell you that you're looking down at about a 45-degree angle. The scale is wrong. It looks almost as if there's 8 different moons going around the Earth. Some people might even believe that. But the more complicated thing is that they're trying to show you 2 things here. They're trying to show you the appearance of the moon from outside and also the appearance of the moon from a scene from the Earth. So again, you have to be really careful when you're making diagrams or illustrating books or whatever. So what does happen when the moon goes through the shadow of the Earth? Well, many of you know we get an eclipse of the moon. Here's the one from last year, which many of you would have had a chance to see. So the moon moves through the shadow of the Earth in a few hours. When it's in the middle of the shadow, it takes on a reddish color because the sunlight has come through the atmosphere of the Earth to reach the moon there. So totally different thing, not like the faces. Here's a simple thing here. What color is the moon? Is it white or black? And here the problem is that it depends what we mean by white and what we mean by black. One interesting thing about the moon is that it reflects only about 5% of the light that falls on it, which is about what coal or tar, something like that would do. So in that sense, the moon is black. But as you know, when you look at it way up in the sky against a reasonably dark background, it really does look quite white. But again, that's a relative kind of thing. So you've all seen a full moon, you've all seen a quarter moon, and by the way, here's some terminology. Is it a quarter moon or a half moon? Obviously, it's a half moon, but we call it first quarter or last quarter, whatever. And the obvious thing might be that the full moon is twice as bright as the quarter moon because it's got twice the illuminated area there. But it's 13 times brighter than the first or last quarter. You probably figured that out from looking at just how bright the full moon appears to be when you see it in the sky. But if you look at it with a telescope or binoculars, you can see some of the explanation, and that is when the sun shines on the moon from the side, as it does at first or last quarter, you get a huge amount of shadowing going on because of the craters and the other features on the moon there. So that's the main reason why it's 13 times brighter. Also, direct reflection right back to 180 degrees tends to be a bit more efficient than 90-degree reflection. Here's one that can arouse some interesting debate. If you look at the moon at different phases, you will notice that you always see the face of the person in the moon there, the 2 eyes, the mouth, and so forth. And then you see throughout the moon's 28-day orbit. So does that mean then that the moon doesn't rotate? Well, actually, it rotates in the same period of time as it revolves around the Earth. But again, you can get an interesting debate going because this is a relative sort of thing. Relative to the Earth, it appears not to be rotating. But in fact, from some outside perspective, it's rotating with the same period as its revolution. This is the result of tidal effects over billions of years. The Earth is gradually slowing down as well. So at some time, trillions of years in the future, it will be keeping the same face towards the moon. Here's one that has a sort of conspiratorial side to it. we talk about the dark side of the moon. And some people, or quite a few people actually, think the dark side of the moon must mean the far side of the moon. Well, if you think about the moon going around the Earth at its different phases here, well, certainly when the moon is full, the dark side is on the back. We're seeing the bright side. And when we look at the moon when it's at the new phase, then we are looking at the dark side of the moon because it's the side that's towards us. The dark side is the side that's not illuminated by the sun, and that can be any of the sides of the moon. But Dark Side of the Moon, well, there's a famous rock album by that name, and somehow, as I say, there's a bit of conspiracy theory sound to it. Here's one that all teachers should know about, and that is that the moon is not just visible at night, as you might think, but you can see the moon at first quarter or last quarter if you look at the right time. If you look in the afternoon at first quarter and look in the morning at last quarter. So it gives the students a chance to observe something in the sky that they can look at safely. The sun, of course, is observable, but there's problems of safety in observing it. And then there's a thing called the supermoon. The media picked up on this many years ago. What is the supermoon? Well, the supermoon occurs because the orbit of the moon isn't quite circular. It's such that the moon can be about 10% closer to the Earth or 10% further away from the Earth, depending on where it is on its orbit. And when it's 10% closer, it's 10% bigger and 20% brighter than it would be in normal. But the problem is that you can't really tell this unless you had the two different moons, the supermoon and the non-supermoon, right next to them. Simply because it's hard to judge the size of the apparent size of the moon in any kind of absolute way. On the other hand, the media did pick up on this. It does attract people. Whoops. There, hang on. Hang on. Where are we? There we are. Here we are. So getting back to supermoons, this is what happens when you advertise an outreach event to watch an eclipse of the supermoon on a cloudy night. This is the downtown campus of the University of Toronto. This is what we call the front campus. And we got thousands of people coming out. They had lots of chance to chat with astronomers and look at telescopes, even if they didn't get a chance to look through them. So the point is that supermoon does appeal to people simply because of the name. Here's another misconception. It's a bit more than a misconception. It's actually an optical illusion. And that is that the moon looks larger when it's near the horizon than it does high in the sky. Well, this is the sort of thing that you can test with a simple experiment. You just take an aspirin and hold it out at arm's length, and you will find that the aspirin covers the disk of the moon, whether the moon is near the horizon or whether it's high up in the sky. But this is a well-known optical illusion. There are explanations to why it occurs. If you don't believe in optical illusions, here's a famous one here. Which of the blue circles is the larger one? Is it really the one on the right there? And as you can suspect, the answer is they're both the same size. Here we're definitely getting into a bit of pseudoscience here. And that is the misconception that somehow there's more crime and madness at full moon. And this is the sort of thing that you can easily test by going through police or hospital records. And indeed, there's no tendency for there to be more crime or madness at full moon than any other time. But it's an example of what we call positivity bias. And that is that if something like crime occurs when the full moon is full and visible, we take note of that. But if the same thing occurs and the moon is not visible, then we don't take notice of that. And so it's a subtle effect that we have to be very careful about. And it's something that plagues a lot of medical research as well. When you only publish results that say something does have a good effect and not the results that say that something doesn't have a good effect. Here's another very famous misconception here, and that is why astronauts feel weightless. And the misconception is simply that it's because there's no gravity in space. But we're using the word weightless, and weight and gravity are not the same thing. So let's go up to the space station there and see Chris Hadfield there and ask, well, why does he feel weightless? Well, he feels weightless because he and the space station are falling to the Earth at the same rate, but they're both going sideways at about 10 kilometers a second, which keeps them in a circular orbit around the Earth. I mean, you could be weightless if you went up to the top of the CN Tower and jumped off. I do not recommend that, so forget that I said that. But again, it's a real misconception. I remember going to a space meeting in Switzerland, in Austria, and the Canadian Space Agency had an exhibit there. And just to be a little bit naughty, I went around and casually asked the people who were at this exhibit there why astronauts felt weightless. And the majority answer was that's because there's no gravity in space. Anyway, not the case. Here's definitely a conspiracy theory, and that is that the Apollo moon landings never happened. And about 1/6 of Americans apparently subscribe to the theory that this was all staged in a movie lot somewhere in Nevada or somewhere like that. As evidence, they point out that the flag is clearly visible, even though there's no air and no wind on the moon. But obviously, the US is not going to send a flag to the moon if nobody can see it. So they very carefully put a curtain rod there to lift up the flag so that billions of people could see it. But again, it's typical of many conspiracy theories having to do with the government and government agencies and so forth. So here's another diagram from a textbook here, certainly conveying the idea that the planets are close together and all lined up. Well, what we really have here is a picture of all the planets pulled in together to have their picture taken. But of course, they're never like this in reality. You can make a nice scale model by putting the sun as a beach ball, and then the planets are spread out in different directions by up to 2 kilometers. And then, by the way, the next nearest star is in New Zealand, giving you some idea of the tremendous space there is between the stars. Here's a misconception about the asteroid belt. Maybe you've watched those Saturday morning cartoons in which the cartoon character is trying to make his or her way from Earth to Mars to Jupiter or whatever, and try to plow their way through the asteroid belt, which you can see here is really pretty closely packed. Well, I happen to have an asteroid named after me, and I guarantee you that if I stood on my asteroid, looked around in all directions, I would not see another asteroid at all. There's so much space between the asteroids. But again, a diagram from a textbook here gives us the wrong idea. Here's an even worse example, and I have the feeling that this is actually from a National Geographic publication here. So look at all the misconceptions that we have here. The planets are closely packed together. The asteroid belt is pretty dense here. The planets are going around on things that look like railway tracks. Oh, surely not. Right outside the solar system are the stars and the other galaxies and so forth. So again, totally misconceptions just because of the way the diagram is drawn. Now, for many of you, you remember when Pluto was the 9th planet. So when Pluto was the 9th planet, any possibility that there was another planet out there made it planet X. And as soon as it's planet X, we get the conspiracy theories coming back, and the idea that, well, there's another planet out there that's hiding behind the sun and NASA hasn't told us about it or whatever. Now, as you probably know, we only have 8 planets. So any planets beyond that would be the 9th, 10th, 11th, and so forth. But to deal with the fact that astronomers were finding objects out there that were comparable in size to Pluto, they had to make a decision. Was Pluto to be reclassified? Were all these objects out there going to be considered planets? So a decision was made at a meeting of the International Astronomical Union, which I attended, which decided to draw the line above Pluto. So Pluto and everything below it in size would be considered a dwarf planet and not a planet. So the planets end at Uranus. Okay, many of you would know what this was. It's a comet. And so what is it doing? Well, you might think it's streaking across the sky with its tail out behind it. And that leads to 2 misconceptions. First, that comets streak across the sky, and secondly, their tails trail behind like a cat's. And all you have to do is to look at a track of a typical comet. This is from a few years ago here, but it took it of the order of 2 weeks to go twice the diameter, twice the length of the Big Dipper here. So it took about a week to go as far as you would have to go from one end of the Big Dipper to the other. But you'll also notice that as the comet moves here, the tail is pointing not behind the comet, but in front of the comet. Certainly not anything that you see on a typical cat. Apparently, Tycho Brahe was the first one to announce that tails of comets can always point away from the sun, no matter which way the comet is going. Though I suspect that there were Oriental astronomers that had noticed that before the European astronomers like Tycho did. But we call it a comet tail, which of course implies that it's on the back end, even though it's not. So the streaking probably comes from another phenomenon, namely meteors, or as they're sometimes called, shooting stars or falling stars. And believe it or not, there are people out there who think that this has something to do with stars, even though, as most of you probably know, they're little bits of space dust that encounter the Earth's atmosphere, fly through it in something like a second or two, giving up their energy and producing the light that we call a meteor. Now, I showed you that diagram from National Geographic that gave you the impression that the stars were just beyond the solar system. And this is a common misconception, that they're just outside and there's no reason we can't send a spacecraft to the nearest other star and so forth. But again, if you actually work out the scale, Proxima Centauri is the nearest other star to the sun. It's about 10,000 times further away than Neptune. Remember the scale model where the nearest other star is in New Zealand. So it's a great distance, and that explains why we need totally different techniques like telescopes in order to study the stars, galaxies, and so forth. Most people would think that the purpose of a telescope is to magnify, simply because in advertisements, they're always touting 999 power magnification and so forth. But what you always have to remember, and certainly people have to remember before Christmas, before they start buying young people trash telescopes, is that a telescope is not really just to magnify, it's to gather light, it's to bring it to a sharp focus, which means that the optics have to be good. Particularly if you're doing professional astronomy or you're doing astrophotography, where you want every bit of resolution that you can. So be wary of trash telescopes that advertise 999 power and so forth. Here's a misconception, and quite a common one, an understandable one. People who look at the sky casually have the impression that all the stars are the same color, sort of a dull white color. But if you look carefully, or if you use your binoculars, you start to see that the stars have different colors. And for instance, Betelgeuse and Orion, the upper left star is reddish. Rigel, the bottom right star, is bluish. And reddish ones are the ones that are cooler, the bluish ones are the ones that are hotter. So it's the opposite to the taps in your bathroom. And one of the interesting things about stars is their color. I'm particularly interested in red supergiants and red giants like Betelgeuse here. They're very interesting and complex objects. So here's another misconception. If I go into a typical crowd and ask them what's the brightest star in the night sky, most people won't actually know, but if they think they do know, they will say Polaris. Well, Polaris is the best known star. It's either number 47, or I checked my observer's handbook this week, which ranks at number 49. I think it depends on how you deal with its variability. Polaris is slightly variable in brightness and so forth. So very useful, very well known, but definitely not the brightest star in the night sky. Now, you may have heard in school or been taught in school that the sun is an average star. Well, it's certainly a normal star, but give the sun credit. It's actually bigger and brighter, more massive than 90% of all the other stars in our galaxy, most of which are what we call red dwarfs. So this is an artist's conception, what you would see from the Earth if the sun was a red dwarf, instead of being a yellow main sequence star like it actually is. We sometimes think that the sun is on fire. That's partly because professional astronomers tend to use the term nuclear burning or hydrogen burning or helium burning, but in fact the sun shines by nuclear fusion, a process which it would be great if we could somehow master here on the Earth. It's actually too hot for chemical burning. Surface temperature is almost 6,000 degrees. Now, during an eclipse of the sun, you may know that we have a total eclipse of the sun coming up in a couple of years, not too far away. So you're going to read lots of stuff about eclipses of the sun. And there's a tendency for people, particularly school principals, to be overly cautious about looking at the sun during an eclipse. Certainly when the eclipse is going on, when the eclipse is fully in full, it's safe to look at it. Before and after, or at any other time, you would not want to look at the sun simply because its normal heat and light would have a burning effect on your retina. But we need to be very careful about the way that we actually describe this. Now, one of the interesting astronomical contributions at UTM is that the discoverer of the first black hole in space, my late colleague Tom Bolton, was actually a faculty member here at UTM in the year that he published his famous paper announcing the discovery of the first black hole in space. This is an artist's conception of what it was like. He was studying the normal star shown here, which is orbiting around a black hole every 6 days. But somehow we get the wrong impression of black holes, partly again because of the terminology that we use, as if it's something that goes around swallowing up everything that comes anywhere near. And if you read the first version of Trivial Pursuit, it will tell you that the end of the sun will be a black hole. Well, just to correct that misconception there, this is what the end of the sun will look like. The sun will swell up and become a red giant. Its outer layers will drift off into space, as you see here. And the core of the sun at the very center there will be a white dwarf star, very hot, but very small. A ton per cubic centimeter of density, a quite remarkable object. Now, moving out into galactic space here, we live in a spiral galaxy called the Milky Way. This is not the Milky Way, but it's a galaxy very similar to it. Difficult for us to take a picture of our Milky Way because we're right down inside it, as shown here. We live in the suburbs of the Milky Way, and the Milky Way has a diameter of 100,000 light years. Now, light year is another term that's used quite casually in everyday life. A lot of people would think it was a unit of time. After all, light year is a unit of time, but it's actually a unit of distance. It's the distance that light travels in a year, traveling at 300,000 kilometers a second. So a very convenient unit for astronomical purposes. Now, in fact, you can show people a picture of a galaxy and ask them what this is. And some people will say it's a galaxy. Some may think it's a solar system in the process of formation, which was actually a general belief 150 years ago. But we now know that it's a system of stars with literally hundreds of billions of stars, like our Milky Way. Now, this brings us to the Big Bang. This is the last but three of the misconceptions that I want to show you. But the Big Bang is the name that we give to the birth of the universe when it expanded from a state of great density and temperature. But there's somehow a feeling that it's like some explosion into an empty room or an explosion into empty space. Whereas that's not the way that our universe works. What Einstein showed us was that matter and space are intimately connected together. A good way of visualizing this, a sort of two-dimensional analog, is by looking at the surface of the balloon and painting some galaxies on it and letting space expand. So you see that space expands, the galaxies move away from each other, but they retain their position on space. So they're not moving relative to the space where they're situated. So very difficult concept, but one which we constantly get questions about. So this brings me to the last three misconceptions, and they're very complicated and very subtle ones. The first is that somehow the positions, motions of the sun, moon, and planets influence human events and behavior. Well, first of all, numerous studies have been done, some of them involving astrologers, and shown that there's absolutely no evidence that astrology has any astronomical basis. On the other hand, it's a bit misleading to say that astrology doesn't work, because if the astrologer is a good counselor, or if you read all 12 horoscopes in the paper and they all have good advice for you to follow, or there's a very powerful thing called the placebo effect, which means that you feel better if you think that you're getting some good advice or treatment. And of course, if you have the sense that you belong to some kind of team. I belong to the Cancer team. I was born in July, but the point is that it's not in the stars. Another widely held belief, and that is, excuse me, that space aliens have visited the Earth, either in the present or in the distant past. Now, this, of course, is a multi-trillion-dollar industry in the media, whether it's TV channels or science fiction movies or whatever. So there's a strong desire to actually believe that flying saucers are real. It makes it more exciting. But whether it's flying saucers or the claims that were made by Eric von Däniken, he was sitting in a Swiss jail, there's simply nothing to it. We always look for evidence. Everything has to be based on some form of evidence. So finally, there's the issue of astronomy versus religion. And that is that according to one interpretation of one scripture of one religion, the universe and everything in it was formed over only 6,000 years ago. But again, the evidence is overwhelming that the universe and everything in it is billions of years old. So the question becomes, how can science and religion actually coexist together? And the answer is yes, they can. I have numerous colleagues who are scientists, and at the same time, they are deeply religious. I have a colleague who is a Jesuit priest, et cetera, et cetera. So there's no need for science and religion to conflict, but we have to deal with, in the case of public beliefs, that there will be some creationists out there, some young Earth creationists that will have trouble with this. So finally, just to sum up here, there are many ways in which we gain information, including misconceptions. Some of them may be perfectly trusted people, like religious leaders or teachers who have their own misconceptions. Many years ago, I actually became involved with OISE because we were studying the misconceptions that elementary school teachers had when they set out to teach astronomy in the curriculum. The media, do we trust the media? Well, you can answer that for yourselves. Always the best thing is to try and engage in some critical thinking, some investigation, some research by yourself. It's a problem that our whole society faces now. Too much fake news, too much misinformation about things that are frankly much more important than astronomy is. Too much suspicion of government, of science, and of academics such as myself. So the bottom line again is evidence-based science, critical thinking is absolutely crucial to our health, our environment, and our planet. And I always end my presentations with this slide here from Gary Larson. Mr. Osborne, may I be excused? My brain is full. So that's what I have to say, and I hope that you have some questions, and maybe there's some in the chat. I'll leave it to Randy.
Thank you very much, John. That was excellent. All right, there we go. All right, gonna have to work the kinks out. All right, John is back and John can answer questions. So probably the best thing is to yell them and I will repeat them. Okay, let me just check chat. I don't see many questions in here, so Joe.
So, I don't know if John can hear me, but going back to his slide about do all stars blow up and become black holes or neutron stars or whatever? The question, and I feel justified answering in asking this, because you had talked about how we are on the
Joe?
edge. Yeah. Okay.
If you have a question, come on up. It might be a little easier.
Okay, so yeah, I feel justified in asking this because, as you mentioned, we're kind of on the leading edge of introducing astronomy to the masses. But the question is, why is it that, let's say, blue giants or some of the larger stars that do blow up into black holes or neutron stars, why don't they become planetary nebula? Why don't they fizzle out the same way? What is the mechanism by which they, and I know it has to do with the size, but I don't know anything further than the size.
Well, they die much more violently. So for a supernova, for instance, when the star runs out of energy, the core collapses within a very short period of time, releasing huge amounts of energy, which blasts the outer layers of the star out into space to produce what we call a supernova remnant. So at the very core of the star is usually a neutron star. A neutron star is maybe 1 to 3 times as massive as the sun, but surrounding it is this huge nebula of material being blasted out at several thousand kilometers per second. And this is something that the public is always very interested in, because that expelled material has been enriched in the heavy elements like carbon, nitrogen, oxygen, and so forth. And when that forms into the next generation of stars and planets, that's the stuff that we're made out of. But if you take a sample of all the stars in our galaxy, the red dwarfs, which make up the majority, have lifetimes that are greater than the age of our galaxy. So they have not yet had a chance to evolve. And then the stars that are like the sun and a bit more massive, then they evolve over billions of years, produce a planetary nebula and a white dwarf at the center. But only a very, very small fraction are massive enough that they collapse at the end to produce either a neutron star, or if the core is more than about 3 times as massive as the sun, then they can produce a black hole. Anyway, that's a briefish answer. There's a nice section in the Observer's Handbook by Roy Bishop on expired stars. I do recommend it.
So just follow up on that. So the only factor that contributes to a star supernova is the mass of it, is the initial mass.
I'm having trouble hearing.
Yeah, the question was, so the only thing that really contributes to the supernova is the mass of the star? So a star has to have a certain mass to be able to become a
The
supernova.
mass of a star determines how it's going to evolve. If the mass is very, very small, it creates its energy so slowly that its lifetime is trillions of years. If it's something like the sun, its lifetime is maybe 10 billion years. It ends up as a white dwarf, a planetary nebula, and it's only the very rarest stars that become supernovas.
Any other questions? Yeah, I think there have been several studies, John, about astrology, and it's always been perplexing that it just lives on the way it is in the popularity. So what do astronomers think about it? Do they just sort of push it to the side, or do they get a little bit frustrated when they're always asked astrology questions at say public outreach events?
Well, I try to give what I think is a fair answer, and that is that the evidence based on many different kinds of studies doesn't support astrology of having any astronomical basis. But there are psychological reasons why a person who follows astrology and reads their horoscope is going to feel better about it, is going to come out of it with a positive feeling. But again, it's not in the stars.
Okay, Alan.
I have a tangential question, not really a misconception, but you've been involved with astronomy for a long time. At what point in the development of gravitational wave astronomy did you start to think that it might actually work?
Oh, that's a good question. I mean, if you follow Einstein's general theory of relativity, then you would tend to think that, well, when we eventually are able to build a gravitational wave detector, we should be able to detect something if it's sufficiently sensitive. And so the answer was that about a decade ago, finally, a gravitational wave detector was built that was sufficiently sensitive, and lo and behold, it started to detect things. Not necessarily exactly the things that we would have thought of first, but anything that rattles the fabric of space-time is going to produce gravitational radiation. It has an interesting history in that there was an astronomer by the name of Joe Weber who was the first one to try seriously to detect it. And he tried very hard, but as it turned out, his equipment was many orders of magnitude too noisy for him to detect anything, but he tried hard. And often that's the way that science proceeds. Someone tries very hard, but the instrumentation is simply not available at the time that they tried.
Ron? Speak loudly.
I can't remember the name of the telescope, but Jamie Matthews was part of launching a scope that looked at one star, or maybe they did several, but one star at a time for months at a time.
Most, yeah.
What's that?
The most satellite.
Most satellite. I've heard of this called the Hubble Space Telescope as well.
Humble.
Hubble Space Telescope.
Yeah.
But my question is, to me, that would be an excellent investment, and also find maybe transits from more stars for exoplanets. And I'm just curious to know why hundreds of them haven't been launched, and just piggyback on other launches like Elon Musk is throwing tons up there all the time, and just get a whole bunch of them up there and monitor 100 stars. And I'm just curious to know, to me, that would be economically big return for little money.
Well, I guess you need a range of different instruments up there. There was MOST, that stands for microvariability and oscillations of stars. It was specifically designed to be very sensitive to the brightness of a star and to be able to monitor those changes over many months. Now, the successor to MOST was a series of 6 shoebox satellites called BRIGHT. The acronym is for Bright Star Explorer, not very imaginative, but these were quite inexpensive. The costs were maybe $100,000 for each of them, and they were launched all together on a single rocket. A very good project for graduate students. They were done at all but one was done at the Institute of Aerospace Studies at the University of Toronto. But then the question is, do you really need more than a handful of satellites to do this kind of thing? Because there are other satellites that measure star brightnesses, things like TESS and so forth. And even the Hubble does a certain amount of things of that nature. But it's amazing the wide variety of different instruments that are around, and it's not just Hubble, it's not just Webb. My department chair, Bob Abraham, who would be an excellent speaker, by the way, he and his colleague from Yale have developed a satellite called Dragonfly, and it's an instrument called Dragonfly. It basically consists of several dozen high-end telephoto lenses that are networked together with computers and can actually see structures that are 10 times fainter than anything that Hubble can see. And this is for a cost of less than $1 million. So Canadians are known for being creative. We have a wonderful project called CHIME, which is a radio astronomy project. It's just won a major award from the Natural Sciences and Engineering Research Council. University of Toronto is one of the universities that's heavily involved in this. But it's just one more evidence of the range of creative things that are going on, but you may not necessarily hear about them in the paper.
Keith,
Any thoughts on what accounts for the persistence of misinformation? Just laziness, stupidity, are people actually profiting from telling strange stories? Or
Are they profiting from it?
is it just that part of the game of some sort? I mean, it seems to be ever more present that you hear out more and more outrageous things.
Mhm.
Accounts for how common the outrageous is and what a challenge you have trying to promote more factual information.
Well, I mean, all I know of is these channels, particularly in the US, that cater to far right-wing audiences and that make huge amounts of money for the people who run them. And there's a case that's been in the news for the last few weeks there involving the school shooting being labeled as being totally non-existent. And finally, somebody managed to sue this guy and his operation for close to $1 billion. Now, whether they'll ever get it, I don't know. But what it illustrates is that this kind of content earns huge amounts of money for the people who put it on. I mean, that's why the belief in flying saucers and so forth is so prevalent, is that by making movies or TV series about space aliens, you can generate huge amounts of revenue from advertising.
yeah, maybe last question.
And I guess astrologers make a living.
So do the school shootings happen more often? I'm just kidding. I'm just teasing, following up. So, my question since you brought up planning at the visionary universe, I want to know which version of the multiverse you subscribe to, or if any, and switch that over.
This,
Well, multiverse, this is one of
this version.
Okay, so let's see what the big version is.
So which version of the multiverse do you subscribe to, John?
Theories of stuff out there on the physics.
I'm very conservative. I don't think about multiverses. I remember that universe is defined at everything that is. And so for me, for the time being, until the evidence is stronger, it's the universe that we know and love.
Okay, so mathematically, there are evidence for, based on.
But remember that we don't know what occurred before the Big Bang. If anything, it's simply beyond the area that we can get evidence about. So who knows?
You believe the observable universe, okay, that's
Okay, well, John, thank you very much. We all appreciate your time.
Okay, thank you very much. And I'm glad that you're back at UTM, and one of
I'm
these,
sorry.
I hope to be there in person.
Oh, yeah, next time, definitely.